All right, in section 3.2, we are going to take a look at polynomials. So first, let's jump into some vocab. So a term is just a single number or variable, or it could be numbers and variables multiplied together. So some examples of a term could just be 2 or x squared or 3xy to the fourth z to the 90th. This thing would be one term. Okay, this entire thing would be considered one term. Right, just numbers and variables being multiplied together. The degree of a term then is the sum of the exponents on the variables. So for example, if my term is 2x squared times y, the degree of this term is 3, okay? Because even though we don't see the exponent on y, we know it's a 1. So if we were to add up the exponents on the variables, we would get 3. Now, the leading term of a polynomial is just the term with the highest degree. So if we take this polynomial of 2x minus 7x cubed plus 4, the leading term would be this negative 7x cubed, okay, the thing with the highest degree. A leading coefficient then is just the number in front of the leading term, or the coefficient of the leading term. So if we take that same polynomial, since we said negative 7x cubed was the leading term, negative 7 would be the leading coefficient. And then finally, the degree of a polynomial is just the degree of the leading term. So again, if we take that same polynomial, since negative 7x cubed was the leading term, the degree on that is 3. So we would say the degree of the entire polynomial is 3. Right? So let's look at a few examples here. Right? So let's look at this first polynomial. Okay, this just has one term. The degree would be the sum of the exponents of the variables. So the degree here would be 5. The leading term, well, we just said this is all one term, so the leading term would be negative 10r cubed x squared, and the leading coefficient would be negative 10. All right, now for my second example, the degree would be 4, the leading term, negative 7x to the fourth, and the leading coefficient, negative 7. All right, so why don't you guys try this next one? So the degree would be 3, because this would be my leading term, right? The square root of 2x cubed. So the leading coefficient then is the square root of 2. Now, this last one looks a little bit different, okay? But if we're only concerned with finding the leading term and the degree and the leading coefficient, we don't need to multiply this entire thing out, okay? But it might help if we just kind of think about what this means, right? This means I want x minus 3 times x minus 3 times x minus 3 times x plus 1. So if all I care about here is finding the leading term, well, that would be multiplying the x times the x times the x times the x, right? So what I end up with is that this is going to be a 4th degree polynomial. My leading term would just be x to the 4th. I'm just multiplying x times x times x times x. Now we could do that without writing all this out. We could just think, well, I'm going to take x cubed and multiply it times x to the 1st. The leading coefficient then, the number in front here, would just be 1. Just a little bit more vocab. Depending on the number of terms in a polynomial, we have a few different names. Right? If we just have one term in our polynomial, we call that a monomial. If we have 2 terms, we call that a binomial. 3 terms, we call that a trinomial. And then anything after that, 4 or more terms, we just call it a polynomial. Technically, these would be examples of polynomials as well. We just have special names if we have 1, 2, or 3 terms. Then, if our polynomial is first degree, we say that is a linear function. If it's second degree, it's quadratic. Third degree is cubic. Fourth degree is quartic. Fifth degree is quintic. And then anything after that, we just say sixth degree, seventh degree, eighth degree, and so on. All right. So some common properties of polynomials. First, the domain of every polynomial is all real numbers, negative infinity to positive infinity. Right? If the domain is not all real numbers, it is not a polynomial. In terms of the graph, we say it is smooth and continuous. So to break that down a little bit more, that means no corners, no cusps, and no breaks in the graph, right? No jumps or asymptotes or anything like that, right? The graph is smooth and continuous. There's never division by a variable, and the variable's exponents can only be whole numbers, all right? 0, 1, 2, 3, 4, and so on, all right? So let's look at a few examples that are not polynomials and kind of get a better understanding of these different things here. All right, so in this first, or the first two, we're just given functions. I have 3x minus the square root of x. Well, one way to look at this, okay, if we remember what exponents mean, a square root is the same as the 1/2 power. So we said the exponents on a variable can only be whole numbers, right? So this would not be a polynomial because we have a non-whole number exponent, okay? So I'm just going to write my reason is 1/2 exponent. In my second example, I have a variable in the denominator, right? The reason we can't have variables in the denominator is that this is going to lead to discontinuities. So here, this is not a polynomial because we are dividing by a variable. Now, in our two graphical examples, this right here, this is called a cusp. It's like a super sharp corner. An example of a corner would be something like the absolute value function, right? Something that's a little bit more pronounced like this is called a cusp. So this would not be a polynomial because it has a cusp. It is not a smooth graph. And then finally, our last example, we have a break in the graph. This is not a polynomial because it is not continuous. All right. Now, the next thing that we want to talk about is end behavior. End behavior just talks about what a graph is doing as we go really far to the left or really far to the right. Are we going up or are we going down? The end behavior is determined by two things, okay? By the degree of the polynomial and the sign of the leading coefficient. All right. So if my polynomial is of even degree, right, so that could be anything like x squared, x to the fourth, x to the sixth, x to the eighth, right? Anything where my leading coefficient has an even power and my a value, meaning my leading coefficient, is positive, this is what my end behavior is going to do, okay? My graph is going to go to positive infinity. Now, the way that we write this out, okay, we're going to say as x goes to negative infinity, right? So I'm going to the left, f of x goes to positive infinity, right? F of x meaning the y values, the function itself goes up. Then as x goes to positive infinity, f of x is still also going to positive infinity, right? The graph is going up in both directions, and that is true if we have an even degree and a positive leading term. So like, x squared, x to the fourth, so on. If I have an even degree but a negative leading coefficient, so like negative x squared, negative x to the fourth, so on, my end behaviors go down like this. Okay, so the way that we would write that, let me get a different color here, we would say as x goes to negative infinity, my function goes to negative infinity. And as x goes to positive infinity, my function goes to negative infinity. Okay, so the first part of these statements is talking about left and right, right? So this is saying as x goes to the left, y goes down. And as x goes to the right, y goes down. Now, for odd degree, right, so this is like x to the first, x to the third, x to the fifth, and so on. If my leading coefficient is positive, my end behaviors will look like this, right? And again, this means what's happening on the end. This doesn't tell us anything about what's going on in the middle of our function. This tells me what's happening at the ends. So here, we can say as x goes to the left, as x goes to negative infinity, my function, the y values, go to negative infinity. And as x goes to positive infinity, right? So as x goes to the right, the y values are going up. So the y values go to positive infinity. And finally, if I have an odd degree and a negative leading coefficient, then as x goes to the left or as x goes to negative infinity, my function is going up. So as x goes to negative infinity, f of x goes to positive infinity. And as x goes to positive infinity, meaning we're going to the right, the y values are going to negative infinity. All right, so let's look at a few examples of this. All right, so just given a function, right, negative x cubed minus 2x squared plus 1, we just want to look at our leading term, which is negative 2x cubed, to determine our end behaviors. So we can say as x goes to negative infinity, right, since this is a negative and odd degree, as x goes to negative infinity, right, f of x is going to go to positive infinity, and as x goes to positive infinity, f of x is going to go to negative infinity. Okay, so this entire statement would be our answer, right? As x goes to negative infinity, f of x goes to positive infinity, and as x goes to positive infinity, f of x goes to negative infinity. Now, what that tells me is I know that the edges of my graph are going to do something like this. And we're going to use this property to sketch polynomials eventually. This doesn't tell me anything about what's happening in here. All I know right now is that at the ends, my function is going to do something like this. All right. In the next example, well, why don't you guys try this one real quick? All right, so my leading term is a positive fourth degree, so positive even. That means my end behaviors are both going to be going up. So as x goes to negative infinity, f of x goes to positive infinity, and as x goes to positive infinity, f of x goes to positive infinity. In the next two, we have to think about what our leading term would be, right? So we talked about this on the front of the paper. If I take x and square it and then multiply that by 2x, my leading term is going to be 2x cubed. So this is a positive odd degree, right? So positive odd degree is going to look like this on the ends. Again, don't know what's happening in here, but I know it's going to look like this on the ends. So as x goes to negative infinity, f of x goes to negative infinity, and as x goes to positive infinity, f of x goes to positive infinity. One last one, right? Why don't you guys try this one real quick? All right, so my leading term is going to be x cubed times negative x. That's going to end up being negative x to the fourth for my leading term. So this is a negative fourth degree. That means that my end behaviors are going to do something like this. So as I go to the left, the y's go down, and as I go to the right, the y's also go down. All right, so that's it for 3.2 part 1. The final question is going to pop up asking you what questions you have.